Okay, so we're picking up on day 2 of our study of the exponential function applications. This is still objective 5.3. But today, yesterday our focus was exponential decay. Today our focus is, excuse me, going to be exponential growth. We still will be looking at the equation y is equal to a times b raised to the kt. Okay, where a is an initial value, b is representing how the initial value grows, k is some constant, and t represents time. Okay, so yesterday we did radioactive decay, and we did how light travels through water. Those were examples of exponential decay. Today we're going to start with example 3. And example 3 is an example of how a population of people grows. So we will be studying the Malthusian growth model today. And what we have here is an example of the population growth for the United States. It starts in the year 1790. And then I think the data stopped in 1990. This is just a graph I pulled off the internet, where the little dots here are representing the census. So they went around to everybody's house in the whole United States and said, how many people live here? And they added it all up, and there you had your answer. Okay, and then we're going to be studying this purple line here that represents this model of exponential growth. So as you look at this model of exponential growth, you can see that it pretty much sits underneath the population trend, the actual discrete data, but it follows the trend pretty well. Once it gets to 1990-ish, it bypasses the census, but that happens when societies get fairly advanced. Population will slow down because people will stop having as many children. They don't need as many children to make their world go around. So it's a pretty good data example. And what's important to pay attention to here is that our x-axis down here is representing the time in years. That's important. It's going to come up every problem we do today, that our x-axis is representing the time, and our y-axis will be representing the population. Now, what we have to consider when we're doing these problems is how do we figure out how much a population is growing per year? So we have to keep in mind that we have to take the birth rate and the death rate into consideration, right? Every year a certain amount of babies are born, but there are also a certain amount of people who die, and you have to take that into your calculations to figure out how much the population is growing. So let's take a look at our equation. Here we have our formula for population growth, pretty similar to the formula we talked about at the beginning. Let's define what all these things mean. Okay, so I'm going to get out my colors. So P is your population after time has passed. You just have to, so like in the example, I think this one will be the population at 50 years. So that will be our P. That's what we'll be looking for. Our P sub 0, I'll do that in pink or purple. Our P sub 0 is our population initial, which means at time 0, at 0 seconds, this is the population that we're starting with. So it's your initial population at time equals 0. No time has passed. Your E, you guys know what E is. E is just the natural growth pattern of something that is procreating. It's a fairly universal growth rate. Okay, it's our base of our growth rate. It's not the growth rate. It's the base of the growth rate. And then, so that we know is just the natural growth rate. The way things grow in nature. It's nature. Reproducing. Okay? All right. K is your constant growth rate. And again, we have to take into consideration births minus deaths to get the growth. And of course, if those things flip-flop, then you don't have growth, you have decline. So pay attention to the problems that you're working on. And then T, of course, is your time. And, you know, if you're studying a population of people, then you would probably be measuring time in years. If you were studying the life cycles of mosquitoes, you'd probably be more working in days, right? Or rabbits every month. Just depends on what you're studying. So watch your time units. All right, so let's go look at our problem, and you start marking up and annotating the problem as I read. The population of the U.S. is approximately 275 million people. This is an older problem. It's higher now. So what does 275 million people represent? Initial population. So I think I did mine in purple, so I'm going to get my purple pencil out. And I'm going to mark that P sub 0. All right. Assuming an annual birth rate is 19 babies per 1,000 people, and the annual death rate is 7 people per 1,000 people, what are those two values helping me to develop? The constant growth rate, right? So that's our K. So we're going to have to use both of those to help us find our K. And it says, what does the Malthusian model predict the U.S. population will be in 50 years? So 50 years represents our time. And our job is to find the U.S. population, right, in 50 years. So that's what we're looking for. What's the population at year 50? So let's write our equation, yeah? Population, we can put at year 50. Just to be fancy. You don't have to put it there, you know. Population at year 50. So that's our original population, 275 mil. How many zeros? Right on. Times E, the way people naturally procreate here. Raised to the, you know what, we need to find our K, so let's go over here and find it. Okay, so to find K, we have to do births minus deaths. And of course, we could plug that into the calculator and just tuck some parentheses around it, but why not just do it? It's 19 per 1,000 minus 7 per 1,000, right? Which you can simply do as 12 per 1,000, which actually I would prefer to write as a decimal personally, because the less fractions I have to plug into my calculator, the better off I am. 12 thousandths looks like this. Do you agree? 12. The 2 is in the thousandths place. That's 12 thousandths. So let's plug into our K, 0.012, times our time, which is 50 years. All right. I'm going to move this out of the way a little bit so we have a little more room to see what's going on. So you're going to plug that into your calculator. So I'm going to press pause so you can do that. So you're going to get the answer of 501 million. I should be writing this in blue because this is my population. So the population at year 50 is 501 million 82,670 point some people, but you can't have 0.5 of a person. And I say that you could approximate this, that there would be approximately 501 million people in the population in 50 years from the date that this data was provided. Because of course that data is going to be a little bit off, right? You can't predict exactly how many people there are. You could have like an epidemic and knock out a couple 100,000 people. It could be a little bit off. Or you could just have a generation of people that want to have 5 kids instead of 2, and it could be a little bit off. It's just a predictor. It's not a perfect science. All right, so what you're going to do now is do the next problem. So I'd like to see you set that up, write it down on your paper, and then I'm going to teach you how to use this calculator to copy paste so that you don't have to retype the whole thing in. You just have to change the years. You might already know. With this one, you get the population at year 100 was 913 million and some change. So I'm just going to call it approximately 913 million. So nearing a billion. All right. So there's an example of population growth. Now what we're going to do is we're going to flip over onto the back and we're going to make a couple changes. So I'm going to step forward to problem 5 on the back. And I do want you to make some changes because I wasn't paying attention to the homework assignment when I was typing up the notes and I reordered the examples. So the epidemiology problem is going to be example 4. Write that down. Please change it to example 4. It says underneath epidemiology, it says example 5. Change it to example 4 because in your homework, problem number 28 says see example 4. So you'll have to use this actual problem in your notebook or in your notes to answer that question. All right, so epidemiology is just basically the study of how an epidemic grows. So this is an example here of the Ebola epidemic in 2014. And it's not US data. I'm thinking it has, because there was like 2 people. I think this is the world epidemic of Ebola. And basically what you have to understand here is this isn't an exponential growth. It looks like it at first, right? But then it'll hit a maximum and then it starts to drop off. So how could we talk about what that means? Why does it grow slowly at first, then grow rapidly, and then start falling off? Jonah?
Because all the people who are dying, so there's no one else to contract it.
That's possible. Any other thoughts? Right, there could be a vaccine.
More cases starting to pop up.
Right, that's why it grows. But why does it start to fall off? You think it's possible that we might start quarantining people and not people get educated so they don't go out and spread? Okay, so we call this a logistic function. Okay, so here you have your incubation period where things are growing pretty slow because it's taking a little bit of time for the virus to incubate, and then a lot of people are being affected. They don't know it. They think they have the flu or something maybe. And then all of a sudden, boom, lots of people are sick. And then you get to a certain point where the medical people are on top of it and they're starting to give you information and educating you. And then once you're educated, you can protect yourself, right? So that's what is happening here. So let me erase my page. Boom. All right. So epidemiology is the study of the spread of infectious disease or an epidemic, comma, fix my typo. It grows. Actually, we could put a semicolon, I think. It grows rapidly at first because we don't know what's happening. And then more slowly because we get on top of it and we start doing things to prevent the spread. These situations are often modeled by what you call a logistic function. It can't be exponential growth because you don't have an unlimited, infinite population, which is your y-axis, remember? You have a maximum population. So you can only extinguish the population. It can't just continue to grow past however many people are available. So we have this crazy looking equation which you have to write. I'm going to write it over here bigger so everybody can see it. So it looks like this. P is equal to capital M over this big long information at the bottom. So this is a population maximum. Okay, so it's going to cap off the population that can become infected. 1 plus quantity M over P sub 0 minus 1 times e to the negative kt. So that's the equation that I want you to put over on the right-hand side. And then I think really the only thing that we have to define here will be what is m and what is k. Okay? So over here, I think I'll do m in like a pinkish color. M represents, what do you think? The maximum population. Okay, it's the very top. It's the maximum amount of people who could become infected. Okay, in this case, P sub 0, let's talk about that. I'll do that in a different purple. You can't really tell the difference, can you? I'll do it in turquoise. P sub 0 is the initial infected population. So pretty much before you figure out people what's going on, it's that initial amount of people who are infected. And then K, while it's a constant, is usually provided to you. And in this situation, K is representing, it's a constant. Let me write down that it's a constant first. It's a constant, and it has a lot to do with the incubation period of, because usually if something takes 2 days to incubate, it takes 2 days to incubate, you know? So it's a constant that represents how contagious the virus is. How quickly is it going to attack, or how slowly? Okay? All right. And then, of course, you know what E is, and you know what T is, and you know what P is, right? All right. So we're going to go through this data here and start annotating our problem. You get out your colors and you start color coding. Here we have, in a city with a population of 1.2 million, there are currently 1,000 cases of infection with HIV. If the spread of the virus has a constant of 4/10, so is it very contagious, do you think? Probably has a long incubation period, right? You can have HIV for years before you know. Okay, how many people will be infected in 3 years? So let's go and annotate. 12 million or 1.2 million represents? Nope. That's your max population. That's your max population. You can't infect more than that. So that's your cap. All right. 1,000 cases is representing your population initial infection. At 0 minutes, at 0 seconds, there's 1,000 cases. Okay? Your K is 0.4, and 3 years is your time, right? And the question is, how many people will be infected? So that's going to be your P of 3, right? Your population of infected, your infected population at year 3. So let's write our equation. Our population of infected at year 3 is 1.2 million. Count your zeros, that's 5. When you're plugging it into your calculator, 2. Over, hate to color code things, but 1 plus, we have 12 million, again, 5 zeros, over 1,000, which I think I did in turquoise here. 1,000 minus 1 to e to the negative k, right? To the negative 0.4 times your t, which is 3. Now, some advice before you go plugging this into your calculator. You're going to put a fraction inside a fraction. I suggest, before you start plugging things in, to simplify this fraction here because they end in zeros, both your numerator and denominator, and you know that if that happens, you can just cancel out the common zeros. So you could instead just type in 1 plus 1,200 minus 1. You could even type in 1 plus 1199. E. Yeah? You could. Okay? So when you plug that into your calculator, you should get an answer. I'm going to go ahead and pause. So if you got that correct, you should have the population of infected people with HIV would in year 3 would be 3,313, okay, with HIV. Okay, now what I want you to do is the second problem where you're answering the question, how many people will be infected in 10 years? So you try that one. So the P of 10 should have been approximately 52,000 people. It's a little bit over that, but 52,000 people is an acceptable answer. I think it was closer to 52,263, but you know, give or take a couple hundred when you're talking in the tens of thousands isn't that big of a deal. All right, last problem. Here we go. Backwards, backwards, backwards. Okay, so now we're going to talk about something really depressing, but true, and people should learn. Okay, the Malthusian Theory. We're going to study that a little bit. The Malthusian Theory is based off the population studies of an English economist, Thomas Malthus, who you can see he lived back in the day, like way back in the day. Okay, he believed that poverty and starvation were unavoidable because human population tends to grow exponentially, whereas your food supply tends to grow linearly. So there will be a time, and you can study the past, and you can see these times where the population outgrows the resources, and so that population will either die off or they'll move away to somewhere else and they'll find their resources. All right, so here's an example visually of what that looks like. Again, really pay attention to the fact that the x-axis is representing time. And the y-axis is representing population. I just wanted to show everybody. So you can see exponential growth here versus food resources. When the population outgrows the food resources, you reach the crisis point. This is what we will be looking for today. Okay? This is what we will be looking for today. And we're going to have to use a graphing calculator to find it. Come in. All right, so let's read the problem. Take a look at the formula that we have. It doesn't look any different than our population growth model, but we now have to take into consideration the food supply. So we have the same formula representing how populations of people grow. So let's identify some information. The country with a population of 1,000 people. So what's that represent?
Maximum.
Is it the maximum? We're not talking about an epidemic. The initial population is growing exponentially. Yep, we know that based on the formula we were provided, and has a constant growth rate, right? An annual growth rate of 0.02. That's 2 people per 100 people. You with me? 200 is 2 people per 100 people. Okay. Furthermore, the food supply, measured in adequate food per day per person, is growing linearly according to the formula y equals 30.625x plus 2,000. Okay? Let me explain what this means. The 2,000 is representing at year 0 how many people can be fed in year 0. And then X represents what year we're in, and the slope here is representing how many extra people per year can I feed. So in year 0, I can feed 2,000 people. In year 1, I can feed 2,000 plus 30, 2,030 people. In year 2, 2,061 people. You get it? Okay. So this is our food supply. So for a long time, do I have enough food if I only have 1,000 people and they're growing 2 babies for every 100? What's that? Like 10 babies a year? 20 babies a year. Yeah? Okay. So let's write our equation. The question says, in how many years? Ooh, in how many years? So that's time, right? But on a graph, time is representing what variable? X. So we're going to let our t be x. That's what we're looking for, because we've got to use our graphing calculator. We don't graph on a calculator in t's and p's. We graph them in x and y's. Okay. How many years will it take the population to outgrow the food supply? So we're looking for that exponential growth to outdo the linear growth. So let's write our equations. So for equation 1, we're going to do our population growth equation that says this. Our population is going to be y instead of p. And 1,000, which is our initial population, times e raised to the k, which we already know is 0.02, times x, because that's what we want to know. What year? So that's our unknown. In equation 2, that's equation 2. This is going to be our food supply, and we were provided with the equation y equals 30.625 x plus 2,000. Okay. So what we would want to do if we were solving this by hand is we would set those two equations equal to each other, and we'd try to solve for x. But here's a problem. We have x in an exponent, and then we have x as a base. Without some pretty advanced algebra skills, that's a difficult problem to solve. I would rather use my graphing calculator every day. Okay, so here's what we're going to do. Get your calculators out and follow the steps. Step 1, press y equals and enter the equations that we wrote down on your paper. So 1,000e raised to the 0.02x, and if you're looking for x, it's right next to the alpha button. So just to the right of the alpha button is your x. You can just tap it and it'll type in an x for you. Don't alpha it, just tap that button. Okay, so I'll let you type those in. And then we're going to change the window, because right now your window is, you won't see the graph. You won't see any of it. So we're going to change the window setting. The window setting is right next to the y equals button, right to the, just to the right of it. We're going to put in an x minimum of 0, an x maximum of 100. Remember, these are our times, and an x scale of 10. So we're going to be changing 10, 20, 30, 45, 50, like that. Your y minimum is going to be 0. That's base population, no population. Your y maximum is going to be 10,000. Be careful, that's 4 zeros, type them in. And you'll do your scale at 1,000. So it is going to graph 1,000, 2,000, 3,000, 4,000. Okay? And when you're done, you can just tap graph and take a look at your graph. It should look very similar to the one I put up on the board earlier.
What was the y scale?
1,000. Okay? So your graph should look like that. Your window should look like that. All right. So Now, what we're trying to do is identify what X this is right here. Man, it's really hard to tell. And so we're going to make the calculator tell us, but we have to know what to do. Are you ready? So what we're going to do is we're going to have it calculate the intersection of those two graphs. So you're going to press second, trace, because the second function of trace is the calculation button. And you are going to type in, just tap 5 for intersection. You don't have to arrow down to it, just tap 5. Okay? And now, you're going to answer the question. It's saying, are you on the first curve? Are you on your y sub 1? Look. And your little cursor should be blinking somewhere along your blue graph. Okay? If the answer is yes, tap enter. Now it's asking you, second curve, question mark? Are you on your y sub 2? Is your cursor somewhere on your y sub 2? If so, tap yes, enter. And then it's asking you, do you want me to guess? And your answer is yes, tap enter. And what you have here at the bottom, it says here's your intersection. X is 71.7. What does that represent? Time in years. So in 71.7 years, the population is going to equal exactly the food supply. What does Y represent? Come on, guys, remember? The amount of? No, people. This is your, so there's 4,196 people will eat all the food. Okay? So here's what I would like you to do. On your note page, I would like you to draw just a visual to remind yourself of how to find the answer. And then immediately after you're finished with that, would like you to do problem number 37, because you need the calculator and this problem to answer that problem. Okay? And there. So answer the question. It will take just less than 72 years. 72.